Hi, during my previous video, we covered a recap on level, trend, and seasonality. These concepts are very important to understand linear regression and to understand as well what is stationarity. We are going to cover that topic during this video clip. We are going to focus a lot on the theoretical part of linear regression. And yes, we already covered during my previous video clip like forecasting using Excel and linear regression and other type of equations, and we also look at what is a quadratic trend and a cubic equation as well. So a quadratic equation and a cubic equation, please look at my previous video if you do not understand what is that. All right, so let's go to my full desktop to explain linear regression. So we start here. This is the metaphor that I am going to use today. I have here a laser because what we are trying to do in linear regression is to fit a line across a certain number of observations. Yes, if we have a trend that we can fit in a line, I think we are going to have something called a square very high, which means that that is good. Um, but I will explain that later. What I want you to get from this metaphor is that we are fitting a line. That's why we call it linear regression. All right, the assumptions. So what we are going to do today, we are going to go over the assumptions. This is something that we want to cover. And fitting a trend and a linear exponential and other type of equations. This is a couple of things that we are going to do today. We will look at the seasonal component, and probably we will leave the last two topics for the first lecture in 2021. Yes, so I will see you for that lecture. We will carry on with the topic of linear regression after Christmas. So if you remember my previous video, we covered the example of FDI. You can find this data in Blackboard, yes. So it would be great if you follow my example, and well, it would be great. So the possible goals for a linear regression or time series forecasting using linear regression, note that we are using linear regression in order to forecast the future rather than to fit a line through observations, like probably the different reason from what probably you are going to see in econometrics or other modules. Yes, so the possible goals is time series forecasting. This is the first reason. And the second reason is time series analysis to quantify the components, the patterns, and the noise. Right, so here we have the FDI. So what we are trying to do here, like with this metaphor as well, like an arrow, is to try to fit in this data set the best line. I will try to do it at hand here, the best line that fit this data, right? And that line is going to be the linear regression. During the previous data, also we use 3 years. The goal is to forecast 3 years in the future. So if we have here the data, yes, what we are trying to do is to forecast 3 years. So what we need to do then, therefore, in terms of data partitioning, is to divide the actual data set in two. Yes, this section of 3 years, sorry, 3 years, I'm going to call it the validation period. Yes, this is the first partition. And the second partition, which includes the rest of the data, I am going to call it the training period or the training partition. Right? So that is the idea, guys. After I like train a forecast here, I will compare that forecast with the validation period, and I will get to know the errors. Yes? And with the errors, I will select the best uh, um, the best forecast. That is what we are choosing then evaluation period of 3 years, because we want to forecast 3 years in the future, these 3 years. So the major assumption here is stationarity. Yes. So the assumption is means in general, I'm not going to go very like into the details, is that all the data, yes, your data has like the same distribution, yes, and the same distribution in time, right? So if that doesn't happen, for instance, if you have this distribution of your observations, right, with mean t and variance equal to sigma, right? Yes, we want that this mean and this I'm going to call this mu instead. This mean and this sigma are going to be the same, even if you carry on increasing data set, including points in the future for that series. If the distribution changes, so we have a series that is non-stationary, right? So in general, I will just say that a series, in order to be stationary, needs to have a mu equal to a constant, the variance equal to a constant, and also the data set needs to not to have seasonal components. So I'm going to type here no seasonality. These are then the three main points for a series to be non-stationary. That is why sometimes we use the return. So if, for instance, if you have here again FDI, what we try to do is to try to find the difference of the let's say FDI in time t minus 1 minus FDI in times t, yes, and this divided by FDI in t minus 1. Yes, in doing that, we are trying to find is the change. After like trying to find the changes, we are going to get a data that is going to look more stationary, being this 1, 0. Let's say that if we do perform this, what we are going to get is something like this. Yes, data that is always like fluctuating towards 0. If we have like the same level of fluctuations, yes, more or less, we can say that the data like achieve the sigma, this is a sigma, achieve one of the principles of stationarity. If the mean is 0 is a constant, we will get the other one, and if we cannot see any seasonalities in this data, we can say that this data is actually stationary, right? So what happens if the assumptions are violated? Is more data always better? Well, if assumptions are violated, we will need to use beta estimation techniques, yes, or we will need to transform the data in, the similar fashion. Yes, usually they solve the problem, but if sometimes the data carry on being stationary, even if we use these changes, yes, so we are calculating what is the change rate, if you want, yes, by using this. If the data carry on being stationary, I think what we need to do is to find a different estimation technique. Otherwise, the results can be spurious. Yes, spurious means that the results can be wrong. Yes, and that is seriously bad. Yes, you cannot uh, have that. Right. So what are the principles for modeling time series? So we have the interpretation and parsimony. Parsimony means that a specification is better, or the principle of parsimony says that a specification is better when the specification is more simple. Yes, that is the first one. The second one is the interpretation. So I am going to go to show you like an outcome of a linear regression, and we are going to go over the interpretation. The second one is the goodness of fit. Yes, residual analysis. So in this one, we are going to try to find the best R squared. This is how well, yes, or at what extent our data, our estimation explain the variability of the data, right? So that is what we are going to do. So this is the time series analysis, and the time series forecasting is a little bit different, because what we are going to do is to forecast accuracy, yes, or some cost function, right? And as well, we are going to use as well the concept of parsimony here in order to try to get the best specification. All right, this is a toolkit of regression-based models. So the first one is fitting a trend, linear, can be a trend that is linear. So linear can be something like this, right? Imagine that this is the straight line, but it can be exponential. So an exponential, as you remember from my previous video, is something like this, right? And can be quadratic, right? So remember my previous video about quadratic and cubic like equations. The second one, the toolkit of regression-based models, is fitting a seasonal component. A seasonal component that can be additive, yes, additive is same length, yes, or multiplicative, yes, or like this, right? Um, so we can also fit a trend and a seasonal component, right? And we can capture like special events. So for instance, holidays, right? So we can do this one through the use of dummy variables. Yes, linear regression is interesting in the sense that you can add more variables to your equations. I am going to explain that later. Dummy variables are variables that are 0, 0, 1, right? 1, for instance, when you have the holidays, yes, you will put 1 in your time series, and zeros when we do not have that holiday, for instance. Yes, and we are also able in the toolkit of regression-based model to capture period-to-period correlation. Yes, and we are going to do that later. So so this is the model one for that we are going to study here. This is the basic linear regression model, yes, the linear trend model. The trend is the increase in monthly growth, yes, and we are going to create a running index variable which is in time t, 1, 2, and 3. This is the regression model, and this is something that you need to learn and try to remember, yes. So here we have a yt here is the dependent variable, say e.g. GDP. This one, this beta 0 here is the intercept, right? So the intercept is when you have, oh, sorry, I better plot I think I'm going to plot here down here. Imagine that this is a y-axis, yes, and this is an x-axis, and you have this function, right? This point here is beta 0, is the intercept, yes, when x equals 0, all the x equals 0, you have this intercept. You have a trend model when this variable GDP depends on time, right? So we try to see that because of the time passes by or is increasing, so therefore, because of the time, we are having here a trend, yes. Beta 1 is a coefficient, and this is time, yes, and this is the error. The error is, if we fit here a line, for instance, the error as the differences between this line and the actual values. So the first thing that I did here is to fit model number 1. As you can see here, we fit a model with trend. Yes, I think this is very easy to do in R with the command TSLM, right? And this is the formula that we use, yes. TSLM, yes, trend time series equals the trend, yes. We will do that in a later video. What I would like to stress the fact here is in the outcome, yes. So we have this data, yes, which is especially the training period, yes, and we are training in R, we are training this with a trend, yes. In R is very easy because you just type trend and it automatically will find the trend for these observations, right? We have the following coefficients, right? We have this intercept, yes, the estimate of the intercept is 474, yes, so it should be somewhere around here. This here is 474, yes, 0.3, yes, this one. And the trend is 62.932. This is the coefficient that I was talking about. So if this is the coefficient, right, that means that the data of this line is increasing every period of time in that 62.93, right? As you can see, this is a t-value. The t-value measures at what extent two samples of this data have the same value, 62.93 or 474. If the test is significant, you will find here 3 stars, yes, when it is less than 1%, yes, this number is less than 1% because this is an exponential to the e minus 0.5. That means that this is actually, this number is 0.0000482, right? So it's like we are just saving here all these zeros with this notation, right? So, and the same here, this one is very less than 1%, so you have 3 stars, meaning that this trend is actually happening, is highly significant. Yes, and you can see it here, right? Yes. All right. So in economics, we focus a lot in values that are acceptable to 5%. You can mention like coefficients that work at 10% or less, yes, but they are not great. Great is something to less than 5%. Very good for medicine, yes, is to get coefficients less than 0.01%. Yes, we have here the residual standard error, And especially important here is this R square. Remember that I say that this multiple R square measures how well our regression, yes, how well our regression fits the data or fits the variability in the data. So in this instance, you can see how we have actually a very high R squared, 92%. So linear regression here is actually producing a very good forecast for FDI. Right, so I will stop here and I will use this next slide to explain more the equation that we just have calculated before. So I will see you in my next video. Well, I think we can actually carry on with this last bit because we will use the model number 2 briefly now. So using linear trend model, so the forecast for net investment in 2024, we can find it, yes, if we use F8. Remember the data that we had before, yes, for FDI, F8 is the forecast that we want to make, right? So we use 474, yes, right? 62.93, the coefficients that we are like found here, yes, 474, 62.93, yes, and this equals this value. This is therefore the forecast for time equal 8, yes, meaning this is the forecast for 2014. This is the intercept beta 1, yes, this is the beta 1 is 62.93, yes. So what we can say from this coefficient, because that is another thing that you will need to explain in your projects, what is this 62.93, and the explanation is that net investment of net FDI, yes, increases on average 62.93 billion per year, right? But is this interpretation valid given the model fit? Right? Uh, yes, I think it's very valid since we have actually a model fit a very high square. Yes, as you remember from the previous slide, we have that actually the fit was 92% or 92.24%. Alright guys, so during my next video we are going to cover the model 2, which is exponential trend model. Yes, so we are going to depart a little bit from the linear regression model, and we will try to fit a linear regression with logarithms.